Well, welcome to this evening's Southern Oregon Climate Action Now meeting. What happens with this projector is when the plug comes out, it takes it 2 minutes or so to warm up again. So you'll have to bear with me. I'll just do a couple of introductory things whilst it's warming up. And can we turn the volume up? Are you here? Oh. Okay. Well, indeed. That'll get your attention. Okay, first off, welcome. My name is Alan Journet. I'm one of the co-facilitators. It's coming, Sheldon. Okay, and the other co-facilitator is standing back here, Kathy Conway. And I'd also like to introduce you to members of our board of directors who are here, and I can see at least one, and that's Louise SOCAN. The other two are not with us. Bob is up in Salem, and I'm guessing most people know what's happening in Salem today. So this is probably one of the reasons why we don't have as many orange-shirted SOCANistas as we usually have. A lot of our ensemble are up in Salem, protesting the construction of the pipeline. The Leadership Circle is a group which represents each of the projects that we're conducting, and this is the group that really drives SOCAN in its activities. And we invite anybody to join us at our Leadership Circle meetings, particularly if you're leading a project. We certainly hope that you'll be joining the Leadership Circle. What we're going to do is start with a few project updates.
We're going to do Ray. Sorry.
I'm sorry? We're going to do Ray first. Oh, great. Ray, are you ready? I'm going to do an introduction to Ray Seidler. Ray Seidler, who's sitting right back there, and he's going to come and stand here in a moment, of course, and do the shoe. Ray is one of those folks that Kathy and I count as a very good friend. He's one of the people who's been with SOCAN right from the beginning, and in fact, I think I could say Ray is in many respects the grandfather of SOCAN, because Ray was the primary organizer of an event back in August of 2012, and that was sort of a SOCAN kickoff. Our first meeting of SOCAN formally was actually the next month, but that event was a primer for folks in Southern Oregon to learn what we were concerned about. Ray has also, and I'm sure many of you know this, Ray has also been very instrumental in vocalizing and giving presentations in the GMO arena associated with 15119. So Ray is very much involved in that activity. His background is very simple. He's a retired microbiologist from Oregon State University. And Ray, if I say anything wrong, or that you don't want anybody to know about, just tell me.
It's all on the internet.
And if I recall correctly, Ray was telling me a bit about his background a while ago. Maybe the story has changed since he told me this. He was working as a microbiologist at OSU and then retired from that, is that correct? And
leave of absence.
Took a leave of absence and then started working with the EPA in the regulatory arena. Most recently, he's, as I mentioned, been interested in the genetically engineered organism arena, but right now is working with a group of folks. I don't know from where they're coming. Is it a sort of national, international group?
National.
A national group organizing a conference that's going to take place in September
4th
and 5th in Richmond, which is one of the burbs of the Bay Area of San Francisco. And if I get the title wrong, correct me, is it Soil Without Oil?
Not oil.
Soil, not oil. And the focus of that conference is on how we can make our soils much more healthy if we avoid oil products as much as possible, which means pesticides, herbicides, and so forth. So the focus for Ray's talk this evening is on how we can do something to increase the sequestration of carbon in our soils. As you are undoubtedly aware, the problem that we're talking about is, in SOCAN constantly, is emissions of greenhouse gases. One of the most important ones of those is carbon dioxide, and if we can sequester more carbon in our soils that will help us reduce the problem of greenhouse gas emissions. So would you like to come and grab a microphone and start talking, and I'll get the slideshow going.
Okay.
Yeah, I know. I just put it down. Okay. Okay, should be good.
I think Kathy and I thought we'd have a little fun with the title, and thanks, Kathy, for plugging this title in. I really like it. It's a solution to global warming beneath our feet. Hey, by the way, did you ever throw a party and then get scared whether maybe no one's going to come? So thank you for being here. I understand that there were limousine-type buses that hauled our colleagues' friends up there today. Open bar, lounging seats. Oh no, that was the Koch brothers. Sorry, they just had taxis. Okay, thank you for being here. So tonight is going to kind of be a little bit different talk for me. It'll be both a bridge talk with regards to my interest in GMOs. It'll be a bridge talk, I think, from what you all may be conditioned to hear or have heard about how to put the brakes on climate change. What do I mean by that? Let's get right to it. So are we going to reduce it, or do we sequester it? And if you look closely, there's 4 chimneys up, 7 chimneys, and I think 4 are turned off. That's reducing it. So if you want to sequester it, you do something else with it. It's already out there, and then you stuff it away somewhere, and that's what we'll talk about tonight. And that stuffing it away specifically is going to be done by a biological process. And since I'm a microbiologist and microbes pertain to that process, for some strange reason I felt a little qualified that maybe I could share some information with you. So let's look at this curve once again that we've all seen. It's the increased parts per million of carbon dioxide in our atmosphere over time. And I don't want you just to look at the blue line, but let's look at the red line. And the red lines that go up and down, up and down, up and down, are monthly readings of carbon dioxide over on an annual basis. And this little box here kind of makes it larger. And do you realize that that's a 67 part per million swing in carbon dioxide over the seasons on the Earth? At least these days it is. So what's going on? You're looking at the annual cycle of photosynthetic activity of terrestrial plants. And during the summer, spring and summer, when photosynthesis starts, the amount of CO2 in the atmosphere is drawn down to a low point. And then winter sets in, and photosynthesis generally ceases as the leaves drop, etc., and temperatures cool. And then it's sort of, things go off as they have been. Carbon dioxide increases from all of the ways that we know it increases. So here it is staring right in front of our face. What if we could do something at this low point here with all of this carbon dioxide that's been taken out of the atmosphere? It's already out of it for us. We've done nothing. It's just done by Mother Nature by photosynthesis. And do something with this. Put it away somewhere. So that when the next cycle starts, maybe it'll be another 6 to 7 parts per million. If we really could sequester 100% of that, and I'm not saying that we can. So what I am talking about is carbon dioxide is being removed from the atmosphere by just a miracle process, photosynthesis, and through sequestration. Tonight we'll talk about how it's incorporated into terrestrial environments, plants, vegetation, and soil organisms as they grow. Some scientists refer to this process of sequestration as carbon farming. Okay, many of you have probably seen this chart before from the Department of Energy. Aquatic ecosystems on the right, and it's mainly the oceans here, and terrestrial. Let's take a look at some of the numbers. And I'm going to ask you to remember, and there will be a test at the end of the evening. So in the middle of this, am I blocking your view? Maybe, okay, I'll just stand to the side. So in the middle here in red, we'll see that we have about 9 gigatons these days, 9 gigatons of carbon emanating into the atmosphere from fossil fuels cement production, and land use change. Land use change means building airports, urbanization, etc. Highways, and on it goes. And over here we have a 4. That 4 is the net increase in gigatons of carbon dioxide in the atmosphere. So the difference here, 9's going out, 4 lands in the atmosphere. What happens to the remaining 5? 2 basic things. 3 of the 5 units, 3 of the 5 gigatons are incorporated via photosynthetic processes into plant biomass, and some of that makes its way into soil carbon in the ground, and about 2 of the 9 makes its way into the ocean. And on here there are other numbers that refer to the pools, and let me draw your attention to this number right here. Soils in the globe harbor about 1,500 gigatons of carbon. That's a heck of a lot. In fact, if you took everything from the atmosphere and you added it to everything in the biomass that grows above the earth, there would still be more carbon in the soil. That's a very big number. So tonight, my responsibility, my challenge is to share with you whether or not it's possible to take some or all or more than 4 and add it to that 1,500 number. 4 plus 1,500, that's a very little change. 1/4%. But what we need to do for long-term climate change impacts in a positive way, we need to do it every year, whether it's 1 or 2 or 4 or 6, whatever we're adding, so that 1,500 may go to 1,504, 1,508, 1,512, 1,516, etc. And we're talking about biological processes, which means that ain't going to happen forever, folks. Even if we can sequester, we'll fill up the bottle eventually. So what I'm going to tell you tonight isn't a cure-all for climate change, but it's one of the appendages, in my estimation. Here's the same data, and you're looking at it a little differently. Graphical, below the line is sequestration, above is what goes out, and briefly, you know, it goes into the ocean, it goes into the atmosphere, and the rest, which is not directly measurable very well, but the rest, I'll say, is assumed to go into the terrestrial ecosystem. And what we want to do is, can we make the green larger, more carbon in the soil? Can we make the blue atmosphere a smaller number? Okay. This slide is meant to show you that you can only stuff so much carbon into soil, and here it is saturated. So this is years. This is increasing percent carbon in the soil going up, and this is called an equilibrium. This is called an equilibrium if it was to stay and we weren't adding carbon. So it shows that after roughly 80 years, I know it says 100, but after 80 years that soil fills up. It's a biological process and you can't put any more of that carbon into the soil. But I want to make it very clear how complex this situation is. That's one soil. There are hundreds, if not thousands, of different kinds of soils around the world, all in different habitats, environments, and they don't all behave like this. This soil says, I can double the carbon. There are some soils that say, no, I'll take 20%. There are some soils that say, yeah, I can take 500%. So it's all up to the scientific community to figure out how to make this work and where we can stuff most of the carbon. And that's a process that has relatively recently begun. Professor Ratan Lal is a internationally well-known scientist, professor at Ohio State University, and I consider him to be the father of the modern movement in soil carbon sequestration. And in a landmark paper, it's just referred to all the time, he published 11 years ago, he claims, geez, you know, we can only stuff in about 20 to 40 gigatons into the world's soil. In the last 11 years, a number of scientists said, well, Ratan, I'm sorry, you underestimated. We can do better than that, which is certainly good news. Maybe we can kick it up to 30 to 60, maybe even more gigatons. So you remember that 4, and you remember that 9 number in an earlier slide. The 4 is the net amount of CO2 that goes into the atmosphere. And if we could stuff 60 gigatons, 4 to 60, that's a 15-year time interval which we can have to work out, find out other political scientific ways to slow down CO2 emissions. 15 years we can buy with no equivalent net increase in carbon dioxide. Maybe. The bad news that Lyle also stated in that paper is this is a biological process and you can't stuff the bag quickly. We can only do 5, 10, 15% of that number, the 60 gigatons. We can only do 5 or 10, 15% of that a year. So if we do 10% a year, it takes 10 years to get rid of one of the key numbers for emission. Gets rid of the 4, gets rid of the 9, whatever one we're targeting. 10 years. So we have to do it every year, every year, every year. And we don't know when we stuff carbon into the soil, does it come out again in 100 years? Does it come out again in weeks? Or what? But for climate change purposes, we want it to stay inside the soil for a long time. There are numerous benefits, my friends, for carbon sequestration phenomena. And I'm going to talk to you about two different topics, let's call it. And we're going to have a long leg part of the presentation, and we're going to have a short leg part of the presentation, and they will all come together in one body. And by that I mean, for you to understand how carbon sequestration works, you need to know a little bit about the biology. That's the long leg. And there are many benefits to carbon sequestration in addition to less atmospheric carbon dioxide. It changes everything you can imagine about the properties of the soil. When we add carbon, and I mean manure, compost, leaves, newspaper, etc., simple stuff to the soil, it increases the water holding capacity of the soil so that if there's a drought, the plants may last 2 months instead of 1 month. We change the physical structure of the soil. We do something to the things below the soil surface, to the life in the soil, and so on. There are many, many, many benefits. And one of those could be sequestration of carbon to modulate global climate. So that's one of the benefits. There are many. So when these so-called things that are referred to are in place, carbon is sequestered in the soil. What are these things? And what do we do in order to keep the benefits into place? So on the left here are 2 soils sliced. This is carbon depleted, this is carbon-rich soil. Notice 2 differences about the carbon-rich soil. One, it has organic matter near the top, a little bit more. That's residual grass, straw, whatever. And it's darker in color. The darkness of the color is from a chemical family called humic acids, and it's just a colored pigment. And it is all nice carbon. That is going to be the good carbon that will stay within the soil for many, many long periods, decades, perhaps even hundreds of years. What conditions are optimal then for soil carbon sequestration? And here's a bridge comment. For carbon sequestration that's good for the things, we need a holistically managed land. That means variety, biological variety above the top of the soil. A variety of plants, a variety of trees, and within the soil, extensive root development of whatever it is that's being grown. And it is an organic system. It's, as I said, biologically diverse. Don't till it. Don't add synthetic chemicals. That means it's completely counter to American agriculture based upon genetically modified organisms that necessitate fertilizer, such as nitrogen, phosphorus, sulfur, etc. And by definition, you gotta apply chemicals. herbicides, insecticides, and so on. That's not a holistically managed piece of property. It's not optimal for carbon sequestration. It's deep plowed, typically, has typically one kind of a crop, such as the GMO crop, or unfortunately, I will tell you, it could also be a forest of GMO trees. Monoculture, pesticides. What do we do to get from the orange to the black? Consider apply manure, apply compost, or grow cover crops, as they're called. Those crops will eventually be cut or die, the leaves fall, the roots die, there's a residue that undergoes decay through microbiological processes. And that decay will lead to humic acids eventually that will last for decades and longer in the soil. And then you have sequestered carbon, not only for the benefits, but you have sequestered carbon in addition to modulate climate change. So right to left, dies, residue, quickly decay, some of it stable. That's going from your right to the left over here on the two soils. And as I just said, there are fractions of soil organic matter, those that burn up metabolically and go back up as carbon dioxide. And then there are the humic acids that turn over very slowly. Looking at it again through a slice in the soil, I want you to know, because it will come up in a few minutes later, this is really important to remember. We've arbitrarily designated 3 zones in this soil, 0 to 10 centimeters, that's just 4 inches. It has a lot of organic matter, if you especially have added some to the surface. Most of it stays near the top, and it is metabolized quickly and goes back into the air as carbon dioxide. Further into the soil, there's less organic carbon, perhaps 25% of the total, and it may oxidize and go back into the air in a matter of a few months. But deep down into the soil is the good stuff for modulating climate change. It's a minority, about 20% of what you've added at the top, and it lasts. So if you were a scientist and you wanted to study, geez, can I sequester some carbon in this soil, as we'll see later, wherever you are in the world, what am I going to measure? That's the state of the art. Am I going to measure in the top 4 inches? No. Why would you do that? Because it'll be gone in a matter of months. Am I going to measure in the top foot? Maybe. Am I going to measure down deep where it's important with regards to climate change modulation? You better do that, because that's where you sequester the stable carbon. Looking at this same information a little differently from a graph, here we have soil with increased organic carbon. And this is the depth down into the soil. And these are the same soil with 3 different crops that have been grown. 3 different managements, one crop. So look at this, 50 plus units of organic carbon right near the top of the soil on this management, 10 units way down here, just 20%. What's the difference between these 2 soils? It is based upon modern agricultural principles. The soil with the lowest amount of sequestered carbon is modern agriculture. Go figure. The soil with the highest concentration of organic material is a pasture that hasn't been touched for 15 years. So if it's tilled, you burn out the carbon. When you plow soil, you flip it over and you expose material to the air. The bacteria in the soil say, I can breathe again, and look at all of this organic matter I can chew up quickly in the presence of the oxygen. Okay, I have a 2-minute warning. They're going to change. Dave's going to change the tape or something like that. And I'm going to stop while he does that. Dave, how long does that take?
We're fine for up to 5 minutes,
5 minutes? Okay.
2
Let me
minutes.
finish this slide and then I'll stop. Almost there. So, microbes are active, they kick out the carbon, and the farmer is left with none of those benefits that I listed on the earlier slide. Poor water retention, low organic matter, not sustainable system, requires fertilizer, requires pesticides, etc. when you plow the soil. You'd think that would be something that our farmers in this nation, with all of our extension education universities, would have figured out before 1995. Because that's when the change came. So I'm going to stop on that while Dave will do his thing. You tell me when I can start again, Dave, and I might as well